NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, folks, wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman series. The Von Karman Talks are a monthly opportunity to engage with you, the public. This is your space program. Now, as a reminder, if we have any technical difficulties, we ask that your patience as we get them sorted out. Because tonight, we get to celebrate an anniversary. The Mars 2020 rover Perseverance has been on Mars for the past year. There's a lot to get to talk about tonight, so let's get started. I'm going to first introduce our questions co-host, Nikki Wyrick. Hiya, Nikki.
Hi, Brian. It's good to see you. For those of you joining us this evening, please remember that we want you to get involved in the conversation. As Brian said, it is your space program. So whether you're following along on YouTube, Facebook, or LinkedIn, put your questions in the chat to our diligent social media team, and we will get to as many as we can. If you don't see the chat, make sure to refresh your page, and you should see it then. Back over to you, Brian.
Thank you very much, Nikki. Now we have two incredible and accomplished speakers this evening, and we'll be sprinkling in your audience questions throughout the talk. Our first speaker holds a bachelor's in aerospace engineering from the Massachusetts Institute of Technology and a Master of Science degree in the same from the University of Southern California. In the 30 years since her initial hiring here at the Jet Propulsion Laboratory, she has held critical engineering leadership roles on every spacecraft to have roved the surface of Mars. She joined the Perseverance team in 2015 and has held several leadership roles during the development and operations of the mission. She is now the project manager of the Mars 2020 Perseverance rover. Please welcome Jennifer Trosper. Hiya, Jennifer.
Hi, Brian. It's great to be here, and it's a fun day to be here on our 1-year anniversary.
Thank you for being here on this fun day. Thank you for taking the time. Let's talk a little bit about engineering, but let's talk about, as you said, a year into the mission. I know it's going to be hard to narrow it down, but what are one or two highlights of this past year?
Well, it is what I call the landiversary, so our 1-year anniversary of landing, and certainly a huge highlight of the last year was February 18th, 2021. So let's go ahead and play the video to remind us of that awesome day.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
I've seen a lot of change, been through a lot of pain. Some things are not the same as they were a year ago, but all will be okay. I move on each and every day. The past is where it stays, way back a year ago. I've changed for the better this time. I thought I would never be fine. I strive just to say I'm alright, and for the first time in a long time I'm alright. I've seen a lot of change, been through a lot of pain.
All right. Well, even now my heart is racing and the tears are welling up in my eyes because I'm just so reliving that moment that was so exciting. And you may think after 5 of these now that it's less nerve-wracking every time, but I almost think it's the other way. When we were getting ready to land Perseverance, we were 4 for 4 for rovers, and we just know that Mars can always hand us something challenging. So even though we were confident, we were humble. And as you can see, it was a fantastic landing. And for the very first time, we were able to take images and video of the rover and the parachute while we were landing. And it's just some iconic images that we'll look at for years to come. So a very exciting time. But in addition to the successful landing, there are a couple other highlights I want to talk about, Brian, if that's all right. The first one I want to mention is what you saw in that video. It was a highlight for me to be able to share that success with people all over the world, and the kids who were enjoying that. It was wonderful. We saw those lights from places like France and Switzerland and across the United States and here at home in LA. And I think for us, it was also more special because the time of the pandemic was really difficult for everyone. It was difficult for our team. It was difficult for all those people. We really wanted to offer something exciting and hopeful. And so the successful landing, it was thrilling for us to be able to share that success with all the people who were there with us and rooting us on. And really, it's a true privilege to bring even just a little bit of hope and joy and excitement to those who shared that landing with us. And that was really a highlight for me. So seeing that video again brings that all back to, we're a team that operate and have developed the rover on Mars, but we're all a team who are looking and watching and trying to understand more about Mars as we do this exploration. And then the other highlight, I would say a lot has happened in that first year, and Katie and I are going to go into more of those details. But another highlight of the year, and I've been the project manager for the last 9 months, is really just being a part of this Perseverance team. And if you go to my next slide, I want to talk about something for just a minute. In this image, this is on the inside of the rover's left wheel, front left wheel. And what you see are at the bottom, you can see the white treads of the rover and what they would look like and what they do look like when we drive on the surface of Mars. And above that, you see those treads twisted into a DNA form. And that's really to remind us of 2 things. And the first thing is that all of our robots are of human origin. And the second thing is that the humans are the real explorers. And speaking of humans, I want to bring up the next slide, which shows just a small set of the thousands of people who have contributed to making this mission successful. And over the many years I've worked on these missions, I've become more and more aware of how every individual in this picture is actually uniquely gifted and can do amazing things. But when groups of people like this come together and work cooperatively, work collaboratively, work with technical excellence towards a common goal, that's when you do the impossible. And for me, it's been the privilege of a lifetime to be a member of this team since 2015 and to now be leading the team as the project manager. And the people that you see here, they're my heroes, they're my inspiration, and they're really my lifelong friends. So those are my highlights of the year, Brian.
Yeah, very good highlights. Something you've mentioned and you hinted at a little bit. You've done this 5 times. Each particular mission has its own specialties, but what are some challenges of this one in particular with everything that you kind of already know about Mars?
Yeah, well, this was really challenging from both an engineering and a scientific point of view. We had to build a whole new sampling system. That sampling system had to acquire rock cores intact. Previously, we had a powdered core. And then we had to store them for later return to Earth. And that was a whole new challenge. We had to develop a lot more hardware. And then to top it off, we had to do the mission at a pace in order to acquire 3 to 4 times more samples and traverse 3 to 4 times faster than we ever had in previous missions in order to accomplish what a NASA headquarters set out for this mission and get the science that we wanted to get. So when I joined the project back in 2015, that was the first thing I started thinking about with the team. How can we build this capability to get, it was really 20 samples and 15 kilometers in a 3-year time frame on Mars. And so one of the main things we did was we looked at where we could put significant autonomy into the vehicle so it would be smarter. It could do things on its own. It didn't need mission operations in the loop all the time to check things and make sure things were going right. And so there are a couple areas I'll talk about where I feel like we've been very successful in the implementation of that autonomy and how it's played out on Mars. So go ahead and start this next video. The first area is sampling. What we have is an end-to-end sampling system that can go from the beginning, what you see here, where the arm is moving out to place the core, our coring drill, on the surface of Mars, to take a rock core and place it in a tube. The tube is actually inside the drill bit that you see there. And this whole sequence that we're showing you happens end to end, all in a single sol on Mars. So we acquire the sample. Here you can now see the turret rotating, bringing the core back to and docking with what we call our bit carousel. You can see that's where we store the bits. And then you can see that there's a whole nother robotic arm on the inside of the rover. This is our sample handling arm, which takes the tube out of that bit and processes it. And in the processing, what we do is we take an image to make sure there's sample in the tube. We'll talk about that a little later. And we do a volume probe measurement, and we seal it and store it for subsequent placement on the surface of Mars for future pickup, and then return to Earth. So this entire activity is autonomous. Everything you saw here, Percy will do on her own. And the way we do that is we have our flight software with a lot of algorithms, and we have sensors like force sensors and temperature sensors, and then safety limits. So if Percy's on the right path, she hasn't violated any of her safety limits, she does it all by herself. And if she's got a problem, she'll phone home for help. And I'll tell you a little bit about that later too. But many of our samples were acquired in a single sol, not all of them. And so that's just been a real success story for Perseverance this first year. Now, the other area I want to talk about, and this is really a home run success story, and we're just, I think, just on the tip of the iceberg here for what we're going to be able to do for autonomous navigation. Although we had autonomous navigation on previous rovers, we actually did a major overhaul here. We added another processor. It was a processor that we used for the terrain relative navigation during entry, descent, and landing. We used that also on the surface for stereo image processing, which speeds up the rover's thinking quite a bit, thinking about what the hazards are and making paths and planning its paths. But then we also changed the algorithm itself. We had algorithms on previous rovers that were highly conservative. We wouldn't straddle a rock no matter the size. We just wouldn't let a rock go under the belly pan, things like that. So we changed the algorithm so that we were able to make more accurate maps and find more paths. If you let your rover drive over more rocks, you're going to find more paths and be more successful. So go ahead and show the auto navigation video. Here is our first record-breaking auto navigation sol. This was sol 200. This video loops, but what you're seeing are the images that the rover took during autonomous navigation to decide where to drive. This is sped up, but the total distance we drove on the sol was 175 meters. Most of that was autonomous driving. So what we've been able to do so far on Perseverance is drive about 100 meters per hour. And if you compare that to previous missions, the fastest we were ever able to go on Curiosity or Opportunity was less than 25 meters per hour. So we've quadrupled our rate of traverse when we're in this autonomous mode on Mars. And we just broke another record over Super Bowl weekend, a good weekend to break a record. We drove 349 yards. I put it in yards because it happens to be more than either the Bengals or the Rams offenses got on that day. So Perseverance won the Super Bowl. I don't know. Anyway, I thought that was our strategic traverse planner, Tyler Del Sesto, gave me that little tidbit, which I just think is fun to talk about. So, okay, the second challenge I want to highlight is one that we have on every mission, and it sort of always manifests in a different way. And it may sound simple, but it's the fact that the challenge is Mars and being on Mars. And this time it was Mars rocks not being exactly what we expected. And interestingly, on Curiosity, Mars rocks were also a challenge for us. If you followed Curiosity at all, you'll remember there were these very sharp, small, pointy rocks that you couldn't see from orbit. But once we landed, we realized that they were starting to poke holes in the wheels. And so we had to be very careful about the way we traverse, still are very careful about the way we traverse in Curiosity. So Martian rocks are not problem here, but another challenge we've had here. The rocks that we found in Jezero Crater in the crater floor region where we are now so far, they're very weathered. And so that means they're friable and they're loosely consolidated and they break apart. And if you recall, the very first time we tried to take a sample, it was actually not successful. So go ahead and bring up the next image of Rubion. This was our first sampling attempt. On the right side here, you'll see at the top of the right side is an abraded patch. We always abrade the rock to get under the surface, place our science instruments on it, make sure it's something that we want to take a sample of. And there to the lower right, you see this beautiful borehole with a great tailings pile. We woke up at 2 a.m. We saw those images come down. The rover hadn't completed the rest of sampling, but we went back to bed thinking, okay, all we have to do is come in at 8, look at the tube, make sure there's a core in there. And we were very our hands were this far up in the air, almost celebrating. And then we saw the 2 images there that you see on the left. The bottom one is the image that we take inside that adaptive caching assembly that we showed you in the video, where we expect to see a core in there, and you see the bottom of the tube. So there was nothing in the tube. And then the top one is one that we take before we place the bit and tube in the bit carousel. And you can see, so the lighting was not great on that one, but you can also see if you look carefully that there was not a core in there. And so we took our hands down, grabbed our computers, walked to the room, tried to figure out what to do. And we looked around to see if maybe we had dropped it. We looked down in the hole to see if it was in the hole. Then eventually we did some testing on Earth and realized that the percussive drill actually broke these rocks apart, pulverized them during the percussion. We tried different experiments. We found some rocks that we felt like were Martian analogs here and did some different experiments on Earth to see if we could reduce the percussion and be more successful. But the rocks also has some very hard parts, so we weren't able to penetrate. But the good news is we proceeded on with kind of collaboration with the science team for looking for a weathered rock that wasn't quite as weathered. Since then, we've gotten 6 rock samples. They're weathered, but not quite as weathered as Rubion. And so that has been successful. But that was a challenge. And there was also another challenge very similar that came from these loosely consolidated rocks. Back in January, we spent a lot of January, Happy New Year's, I think it was New Year's Day, we experienced another flavor of this issue. And as I described earlier, if Percy's doing fine, she keeps on going, but if she has a problem, she contacts the ground. And so she contacted the ground when we had cored a sample and we were getting ready and putting it into that bit carousel where we take the tube and the bit and we place it in there into this thing called a bit sleeve. When it was doing that, it sent an error message down saying it got to the force we were looking for, but it was about 1 centimeter short of the place we wanted to push that bit into. And so you go ahead and bring up the next image. So what you can see here on the left is a bit sleeve where we were trying to push that bit with the tube in it into, and you can see 2 pebbles down there. And then on the right, you can see 2 pebbles kind of in the middle of that image. And that is actually sitting on the rotor of the bit carousel. So we had pebbles in the system. We were relieved to see those images. We didn't actually know what it was initially, what was causing the problem. We were relieved to see the images because we at least knew what was wrong. I think we knew that we had to carefully get those pebbles out of there so that they didn't jam up the bit carousel in any way. So what we ended up doing is for the top pebbles, we were able to get those out by using the percussive drill just to put some dynamics into the vehicle, and then we moved the bit carousel and those popped out. And then on the pebbles on the right, we drove the rover and those came out as well. So there's always a fun problem to solve on Mars, but we were able to do that. And now we're basically on our way. We're moving, now we're on the road. And if you go ahead and bring up the next image, right after we in fact, on that last one, we went and we did get a core from that rock. We dumped out the core that had gotten pebbles dropped in the bit carousel. We got a core, and then we're moving along an area called R2B Ridge, and you can see that ridge there, and then you can see the sand dunes in the middle, and you see the rover robotic arm in the foreground of the image. And if you look carefully, you'll see an abraded patch that we did here. As we're moving back to the landing site to get kind of the final samples for this area, this science campaign that Katie will talk about, we did an abrasion here just to see if this was the same kind of rock and give us more information for the context of the region.
Very cool. There's so much. I mean, there's just so much, and I know we can't even get all of it into this talk today. So we're talking about excitement, we're talking about challenges. What are some of the things that we've learned operating, and how does that affect where we go next?
Yeah, well, I would say I've been on 5 of these. I know I've said that a lot of times, but this rover is solid. It's a great rover. It's well built. It's well tested. In general, it executes with perfection the things that we ask it to do. This, of course, is largely due to those people I showed you earlier who built it and tested it and continue to operate it, as well as I think the legacy of the teams and the people who came before us. We've just been learning and getting better at this, being more prepared. And so far, the only times we've really had problems were when Mars gave us something a little unexpected. So because of this, we will continue to push the envelope with this rover and this mission. And that includes still regularly using Ingenuity to support scouting. We're adding more autonomy to the vehicle. And our next big exploration is of the delta in the crater that is the area where we expect to find the sedimentary rock. And in getting there, we really have the opportunity to hit the interstate between here and the delta. And we'll really see what our updated autonomous navigation capabilities can do. And I expect we'll be breaking more records. So let me show you this next image, which shows you the traverse. So the green path is, the green is where we are. We actually, if you can see the sand, there's a thumb, which is sort of a sand area called Seta down there. And we went all the way up to the other part of the thumb that doesn't have the green path. And now we're back down to where the green path starts. It's about 1 kilometer back to the landing region where we'll take the other samples, and then another 5 kilometers over to the delta. And we hope to expect to arrive there in late spring. And of course, our main goal here is to cache these samples for future return to Earth. And our initial caching depot will possibly be somewhere in this map, maybe on top of the delta, so a little bit off the map, or it's equally likely that it would be further even towards the edge of the crater when we're ready to deposit that initial set of samples. So we have tons of excitement ahead on the mission, and we hope you'll continue to follow us and join us in all this excitement.
Well, we've got a lot of people following tonight, which is wonderful. So we're going to bring in one of the audience questions now, and then we're going to go talk to Katie for a little bit, and then we'll bring everybody back for some more Q&A at the end. So Nikki, what are they asking right now?
Yeah, so Jennifer, you've talked a lot about some of the great things that have gone on and how you've worked on several of these rovers. And Tony Oranges on YouTube wants to ask you 2 questions. What new upgrades would you want to see on future rovers on Mars? And also, how many years can the Perseverance rover survive doing science on Mars?
Okay, I'll start with the second one. It's actually not an easier one, but it's one where we build the hardware. It has sort of a warranty, just like your car has a warranty, for about 3 years. We test it to all 3 years, but we have enough energy. We expect the hardware to work a lot longer. You can see with Curiosity and with Spirit and Opportunity, all of our rovers have outlived their lifetime. So the 3 years is when the warranty expires, but we expect it to live quite a bit longer. We're confident of that, but we're also humble about the fact that, different things can happen. So we hope to have it, live a decade or longer, just like Opportunity. Those are great missions. And as far as things I would like to see, when I very first started this mission in 2015, because we had this autonomy focus, I remember going into the conference room with the team and I said, we got it. We can't just, code this thing from the ground, which is sort of what we do. We write our sequences and send them up every day. We need this thing to be more autonomous. And I put my feet up on the table and I said, here's what I want. And I pushed the button and I said, do a great science mission and it'll be done, right? And so we're not anywhere really close to that, but getting the rovers onboard autonomy, onboard sensing so that it can choose its own science targets. We're toe dipping into that one. I think our autonomous navigation is very fast, but it is not quite at the limit of what the wheels could drive. So we could still drive faster. Our next missions are getting really close to pinpoint landing. So that's a great one. But then just this idea that the Percy figures out what she wants to do every day to accomplish the science mission that we've given her. So those are my dreams.
What a great setup and a great introduction to our next speaker. Jennifer, we'll bring you back in a little bit. But our next speaker graduated with a BA in Geology and Astronomy from Williams College and earned her MSc and her PhD in Geology from Caltech. Katie's research focuses on the Martian sedimentary rock record, using orbiter and rover image data to understand the evolution of ancient surface processes on Mars. She is a research scientist here at JPL, a participating scientist on the Mars Science Laboratory Curiosity rover, and the deputy project scientist of the Mars 2020 Perseverance rover. Please welcome Dr. Katie Stack Morgan. Hi, Katie.
Hi, Brian.
So much great stuff we've talked about so far, but one we haven't really talked about yet is why Mars?
Yeah, so the Mars we know today is a barren, dry, very cold landscape, not particularly hospitable to life as we know it. But we know, based on our observations of Mars from rovers and orbiters, that Mars wasn't always like that. And Mars was once very Earth-like. And we think that there's a good chance that Mars was capable of supporting life just like early Earth was. And the period of time when Mars, we think, was once habitable was the same time that life was emerging on our own planet. And so we think Mars is a really attractive place to go to look for signs of ancient life, and perhaps the best place in the solar system to look for signs of ancient life. And every rover mission we've sent to Mars has found and discovered and explored habitable ancient environments. And so we think Mars is really a great place to go to look for signs of life beyond our own planet. And the really neat thing and fascinating thing about studying Mars is that in some ways it is so familiar, particularly when we look at ancient rocks and we recognize the kind of environments that we know and see here on our own planet. Yet this is another planet, and it took a very different path over time to look the way it does now. And so there is still something alien about it. And so it's this combination of the familiar and the unfamiliar, and that makes Mars such a fascinating place to look at and to study and to understand.
So let's keep going in a little further. That's a great explanation on Mars. So then why Jezero crater specifically?
Yes, if we could bring up slide 10, we'll see a view of Jezero crater from an orbiter perspective. And Jezero was selected as the landing site for the Mars 2020 Perseverance rover, and this site really has it all. It has habitable environments, both preserved at the surface and we think in the near subsurface. We have, of course, the delta. That's the main target of the mission. We have some interesting units along the inner margin of the crater, and perhaps even some habitable ancient environments in the rocks themselves, maybe the crater rim and the rocks of the crater floor. We also have a diversity of minerals here in this location, suggesting a variety of different processes occurred at this one site. And also this site has the element of time. The rocks here record hundreds of millions of years and give us an opportunity with a single rover to explore a big period of time in Mars history. And so when we look at images like this, we see a landscape frozen in time. But to really bring this to life for you all, I want to bring up the next video. I think it's video 11, to really bring this to life and show us how this site came to be. So here we are 3.8 billion years ago, and we're about to see the impactor that is going to create Jezero crater. So here it is speeding towards the surface, and boom, we have Jezero crater formed. Quite a catastrophic event, perhaps at a time when we had water on the surface. So here we have Jezero crater. It is now here in this landscape. And what we see now is we know, based on what we see from orbit and now on the ground, that water rushed into this crater from at least a couple channels on the crater walls. And here we see it filling up, and we have conclusive evidence that this crater did indeed fill up all the way to the brim. And we know that it actually overflowed. And there aren't that many craters on Mars where we can say that. And so we know that there was water in this crater for geologically significant amounts of time. And here we see that outflow channel. And as we zoom in here, we're going to see over time, of course, that lake dried up. It disappeared. And eventually it leaves us with the fossil landscape that we have to explore with the Perseverance rover today.
I just love that animation. That's so cool. The main question we're getting a lot right now through our chats and our audience watching at home is, what are the biggest surprises that we've gotten from this first year on Mars?
Yeah, and this is a great question for me, because I and many scientists who've thought about landing sites on Mars, we spent years poring over those orbiter images, trying to guess what's there and try to interpret what's there. And so going into this mission, I thought, I've thought of all the possibilities, and it's going to be one of those things that I've thought about, and that's how we're going to explain the rocks. But of course, Mars throws us surprises, and we certainly had that. One thing, thankfully, was not a surprise. And if we bring up slide 12, we thought from orbit that there was a lake and a delta, and you just saw that in the video. And when we got on the ground and we imaged towards the delta deposit, we saw this beautiful outcrop. And this is the kind of outcrop that you would bring a geology class on Earth to teach them about deltas. This is classic delta stratigraphy. And you see the layers in this image. The flat layers on top represent the upper part of the delta, going into those dipping beds as you get into the lake. And then as you get into those flat beds at the bottom, those are the layers that we look at for signs of preserved organics and possible signs of life concentrated there in the distant parts of these lake deposits. And so we were relieved that this was not a surprise. There is indeed a delta. We have confirmed it, and we have beautiful outcrops to show that we have this habitable surface environment preserved in Jezero. But there were still surprises in store. So if we bring up the next slide, slide 13, while we knew there was a lake and a delta here in Jezero, one thing we weren't expecting was signs of pretty active high energy flood deposits. And so that's what we're seeing here. This is an outcrop from the front of the delta, and that arrow there points to a big boulder, and that's an almost 1 meter wide boulder. And so in order to transport a boulder like that and the boulders in the surrounding outcrop, you need pretty high energy, energetic floods coming into the crater. And so we didn't know that that was happening here in Jezero. So we think we had this lake and this delta setting that transitioned over time into something much more energetic and perhaps catastrophic. And that might have been how water had its last gasp here in Jezero crater. If we bring up the next slide, while we had views of the delta when we landed at Octavia E. Butler Landing, seen here again in the orbiter image, we actually landed on the rocks of the Jezero crater floor. And we weren't sure what to expect of these rocks. There were different hypotheses thrown out by scientists. Are they igneous or volcanic rocks formed from magma or lava flows? Or were they sedimentary rocks? After all, we are in a sedimentary basin where we knew a lake was present. And so we have this question. And in this case, the orbiter data doesn't tell you the whole story. So we went into this thinking, you could probably split the team in half, those who thought it were going to be igneous and those who thought the rocks were going to be sedimentary. So the first couple of months of the mission, we were left scratching our heads about this question. The rocks weren't giving us many clues. They were dusty. Their natural surfaces were obscuring the kind of textures you would typically use to interpret the origin of the rocks. But by the time we got down to the location marked here at Rubion, which Jennifer talked about, the first place we took our sample, we had the opportunity to actually scrape through the natural surface of the rock to see what lied beneath. And so if we bring up the next slide, this is this is our first abrasion. And Jennifer mentioned that these rocks have interacted, have been altered and weathered. And that's exactly what we saw here as well. You can see those holes, and those are holes in the rock, and not just caused by wind particle or sand particles blasting the rock. These are actually inside the rock, suggesting that water has moved through this rock and eaten away parts of that rock. But when we looked at this texture, this variation of light and dark minerals, this is pretty diagnostic and conclusive for an igneous rock. And we think it was formed by volcanic lava flows. But the other neat thing about this, where we start to think about habitability and astrobiology potential, is that some of those light colored minerals you see there, those are salt minerals. And those only form by precipitating out of water moving through these rocks. So while we don't typically think of volcanic or igneous rocks as the prime place to look for signs of ancient life, at least here on Earth, given that water has moved through these rocks, there might have been habitable niches in this rock that are capable of supporting signs of ancient life. And so that's pretty exciting to find igneous rocks here. Those are great rocks to get age dates from and learn about processes in the interior of Mars, as well as to have this potential habitability aspect of these rocks as well. And so really exciting to have this kind of discovery. And to answer that question, volcanic or sedimentary, we answered that in the first year of the mission.
That's amazing to have those answers already. So taking those answers, because science is always about what's the next question, what can this teach us? Where can we go from here?
Yeah, so from a science and sampling perspective, and as a reminder, Perseverance is on the surface to collect samples for possible return to Earth. Jezero has been a slam dunk. We have, from the surface, even though we landed on the igneous rocks, we had views of the sedimentary rocks that we know are in the future of the rover and that we're heading to soon. But if we bring up slide 18, you'll see our current sample collection. And so this is the collection of samples that are currently inside the rover, getting ready in the future to potentially come back to Earth. And so we have a fantastic suite of rock samples that tell us again about the interior processes of a planet, the history of magma in the planet and perhaps erupting out on the surface as lava flows, and then a history of the interaction of these rocks with water that might have created the potential for habitable environments, as well as salt minerals that here on Earth we know are really good at preserving signs of ancient life here on Earth, and the same could be true for Mars. And so we've really hit it out of the park in this first year from a science perspective. We've got sedimentary rocks, we've got igneous rocks, and Jezero has really come through on the diversity and the interesting history of Mars as a planet.
That's wonderful. So, Nikki, I know I've got more questions, but what are they asking out there?
Yeah, so we've got a great question for Katie from Dan on Facebook, specifically about what the core samples are telling us. So have any of the drilled core samples produced any evidence of biological material, or will we not know until they come back to Earth?
Yeah, that's a great question, and it's one that we think very carefully about. The bar is really high for scientists on Mars to make scientists studying Mars to make an assessment of a potential biosignature. What I can say about some of these samples is that we have detected organic molecules in some of these samples, and organics are the building blocks of life as we know it. And so there's nothing that we have yet determined to be conclusively biological in the rocks that we've studied. But fortunately, with the potential for these rocks to come back to Earth, we can confirm that whether there are signs of ancient life here in these rocks. So I think we've very much collected a suite with the potential for that. But we haven't yet determined, based on our data collected on the surface, that any of the things that we found in these rocks or the organics we found in these rocks could only have been formed by life. We're not quite ready to say that, but fortunately we can answer that when these samples come back.
There have been so many great questions so far, so let's try to get as many as we possibly can. Let's bring Jennifer back in. Well, we can have Katie and Jennifer both taking questions for a little while. We go. What do we got, Nikki?
Yeah, absolutely. So for this question, I'm going to ask Jennifer to start us off. Joanne on Twitter wants to know, what are your plans for the next year for Perseverance?
Well, Perseverance has about a couple months, as I mentioned, to be driving to the Delta. And so we're almost able to do that. And then we are going to spend a year doing the Delta campaign and the science campaign, which maybe Katie wants to take that. But the things we're doing on the engineering side as well, I said we're upgrading and putting some more autonomous capabilities on the rover. So we're taking that first step of having the rover check its own energy and time availability as a resource. And if it has more energy or more time at the end of a sol, which is a Martian day that we told it to do, it can actually pick from a set of activities and keep going, or it can drive longer. So we're getting ready to put some more of these autonomous capabilities on, which is very exciting for me.
That's great. And Katie, what about on the science side? What are we looking at for the next year for Perseverance?
Yeah, so as Jennifer mentioned, we are just wrapping up our investigation of the crater floor of Jezero. And we, in perhaps just another week or so, we will aim to collect another pair of samples from what we think are these volcanic rocks of the crater floor. And then we are hightailing it to the Delta. As I mentioned, the Delta is our prime exploration target within Jezero, and perhaps the prime astrobiological target within Jezero. And so at the Delta, we are really excited to transition from the volcanic rocks we've been looking at to the sedimentary rocks, the sandstones, the mudstones, the conglomerates. And one of the neat things about a Delta is that it has what it does is you have rivers from outside the crater collecting rocks and boulders from some of the oldest crust on Mars and bringing it to us, bringing it to the rover. So we don't have to rove for kilometers outside to actually see the rocks of the crust of Mars. They come to us. And that's, again, the great thing about a Delta. So we're expecting to have the diversity of the Martian crust here in the Delta for us to explore, as well as those fine-grained layered sedimentary rocks that may be the key to finding ancient biosignatures on Mars.
That's awesome. Thank you for sharing that. It sounds like you've got a full year ahead of you, one full year done, another full year to celebrate in a year. We've had a ton of questions about the geology of Mars. So Katie, I want to ask you, Robin on Facebook has asked, how geologically active is Mars today? And Benjamin also wants to know from LinkedIn, are there any minerals we found unlike Earth?
Yeah, those are two really great questions. And while I typically don't think of Mars as being the most active geologically today, there are actual processes happening right now. They're just not the ones that we necessarily see preserved in the rock record. So the wind blows on Mars. We know that impact craters are still forming on Mars. Mars has a very active atmospheric processes occur, and the environment is very dynamic and very different than our own planet. But from the perspective of things like water at the surface and volcanism, that part of Mars's history is in the very distant past. But there is a modern environment that is still very active, and we have instruments on Perseverance and scientists who are studying the present day active environment of Mars. In terms of the minerals, there have been other places on Mars where we have detected minerals that are quite rare on Earth and very specialized places. So far here in Jezero, the minerals have been very familiar. And I mentioned the interesting dichotomy of a familiar but alien world. And so far, from a mineral perspective, Jezero has been very familiar. We've had the same kind of minerals in these rocks that we expect in lava rocks on Earth, basalt rocks. We have pyroxene, plagioclase, and we have olivine. The interesting thing about olivine, we have rocks here in Jezero with a lot of olivine. And olivine is a mineral that crystallizes directly out of a magma. And it's pretty rare to find rocks on Earth that are really rich in olivine. But here on Mars and in Jezero, we have a geologic unit that is primarily made of olivine. So that's a really interesting kind of rock unit. But so far, very familiar, as well as the salt minerals that we've seen so far, halite, sulfate minerals. Those are very common here on Earth. And so far, the minerals of Jezero have been more on the familiar side.
Well, that's good to know that there's a whole mix of more on the familiar side, but a little bit of rare minerals, if you will, from Earth. I want to switch over, Jennifer, and ask you a question from Goonjon on LinkedIn, who wants to know, what is the one area requiring the most amount of repair or troubleshooting on the rover so far?
Yeah, the rover has been, fortunately, very well behaved. My previous rovers, I would say, took more troubleshooting, so I'm thankful for that. We have a very complex sampling system, and the sampling system, even though it has worked really well, we've had the challenges with the pebbles being stuck in different regions and having to remove those, as well as that first sample not being collected. We've also had, and so those were the biggest challenges. It took us the most time to figure out, where we spend some time really thinking on Earth. We had a couple other challenges. We have some hardware that sometimes will get bit errors, and that may just be the radiation environment, or sometimes solar weather can affect us. So, but in general, those are the challenges. Really, we've had some issues with those rocks in our sampling hardware, and that's about it. Thankfully.
Well, it's good to know. I was going to say, it's good to know the rover's doing just fine up there after its first year.
I will add one, I'll speak for Ingenuity. We've kind of, brought Ingenuity in. We're the communication relay station for Ingenuity. And in January, when we were going through this issue with the pebbles in the bit carousel, we had kind of non-standard dust storms. And those dust storms they put some dust on our HAZCAMs, and they put some dust in Ingenuity's rotors in a way that the next time we tried to spin those rotors, we saw that we had more drag than we intended. And so we actually had to clean those out a little bit so that we could keep flying Ingenuity, but they're clean now, and we just finished another flight. So it's looking good as well.
Well, thanks for that update as well. How did you know they were asking about Ingenuity in the chat as well? So thanks for the update on how she's
everybody
working with the rover.
Ingenuity. Yeah.
So Katie, I'm going to throw this one to you. We've gotten quite a few questions about the Mars sample return mission. But this one in particular is from Jordan on LinkedIn, who wants to know, what would the procedures be to prevent contamination of off-planet samples once they are brought back?
That is a great question, and we have a whole branch of NASA that thinks about that. That's called Planetary Protection, and it's something that we take very seriously. And it starts to cross into the realm sometimes of science fiction, but again, it is something to take seriously, and something we think about when we bring samples from another world, and a world that could possibly support life, and that we know or that we don't know. And so when we think about bringing samples back to Earth, we talk about biocontainment facilities and having the kind of facilities and laboratories here on Earth that we use to treat the most sensitive biological things here as well. And so that's the kind of facilities that we would develop, and that NASA is working with its international partners to develop, to support and house those samples when we get them back. So that's something that NASA and its partners are looking at and looking to develop to make sure that we stay safe and that the samples are safe as well.
Well, thank goodness for Planetary Protection. I think we have time for only one more question. Now, I know there's been lots of questions, so thank you all so much who have tuned in and asked your questions in the chat tonight. This one is for both of you, but I'm going to have Jennifer start us off. Summer on LinkedIn asks, so many cool things are going on. What would you tell a STEM or creative student who really wants to work at NASA? Things they should know. Also, did you always want to work at NASA?
So I'll start with the second part, because I'm actually a farm girl from Ohio, and I spent my summers as a teenager in the fields. Sometimes I was weeding the bean fields, and I was painting the barn roof, and all these great things. And so I didn't necessarily see myself as a NASA engineer. However, my dad had worked in the missile industry back in the Nike Zeus days, and he had some really cool stories, and I just thought, oh, that sounds adventurous. So I ended up going to MIT and getting a job at JPL, which I just thought was the coolest thing. And so, with that background, one thing I will say is, if you work hard and are passionate about what you're working hard on, and you just, you persevere through your challenges, and you have ingenuity on the things you're trying to solve, you could be a farm girl from Ohio who didn't know what NASA was, and you can be the project manager of the Perseverance rover. So there really are no limits. And then the other thing I would say is, just try different things. There are lots of ways you can be involved in the program and working for NASA in these missions. You can, get into the science like Katie. You can do the engineering and autonomy like me. You can do the media and outreach, right? Like Brian and the other folks here. There's so many videos and taking all these images and doing productions. And even we have this great partnership with Hollywood where, they help take our messages a little bit more clearly to the public than sometimes we can do. And so, I don't know what part of it you'd like to do, but there are so many options and opportunities for you to be a part of exploration.
That is some great advice, Jennifer. And I want to give Katie a chance to answer that too, especially because before we came on this call, Katie was talking about how much fun she has working as part of the Perseverance team. So, Katie, what advice do you have for students? And did you always know you wanted to do this?
Yeah, so I've always been interested in, and even going back when I was a kid, I was always fascinated by things beyond our own planet. And for a long time, I thought it was stars and black holes and galaxies, and astronomy was really where my focus was. And I would always look forward to going to museums on school field trips and seeing planetarium shows and that type of thing. So I've always had an interest in that, but it didn't really crisp up in working for NASA until much later, and I think it was a series of decisions I made, like Jennifer suggested trying new things and following your passion kind of led me here. And I, even in graduate school, I didn't know I wanted to do this kind of work, and I was lucky and the timing was good. I found myself on the Curiosity rover that Jennifer also helped to lead. And I realized, wow, I love this work. Working at the intersection of science and engineering and having new problems to solve every day was just so exciting to me. And so I kind of fell into this through a series of decisions and following my interests. In terms of advice that I would give, especially as a scientist, I think the most important thing is to ask questions. And by asking questions about your everyday life, your surroundings, the things people say, that's how you can be an everyday scientist, because that's really what being a scientist is all about, is asking questions and then trying to seek the answers to those questions. And anybody can do it, any age, any place, on any topic. We can be everyday scientists. And so that's what I encourage folks, is just ask as many questions as you can, and there's no such thing as a bad question. So don't be shy about it, and just go for it. If you don't get something, there's a good chance someone else doesn't either. So just go out there and ask questions and question what is around you.
That's such great advice. That's all the time we have for tonight. I want to remind you all to join us next month for when we talk about, it's called Moon Dance, Dynamics of the Moons of the Outer Solar System. But before we say goodbye, I'd like to thank our speakers, Jennifer Trosper and Katie Stack Morgan, for taking the time today to share their passion and their expertise with us this evening. I also want to thank Nikki and everyone behind the scenes who make these talks possible. And finally, a big thank you to all of you who join us every month. We can't do this without you, so stay safe, stay kind, stay curious, and we'll see you in March.